Let us see the common collector amplifier design. So design means we need to know the values of R1, R2. This is R1, this is R2, this is RE. Sometimes we call it as RL also. So which we are connecting it over here for the transistor circuit in the format where I give input at base terminal. This is my base, and I collect the output across the empty terminal. So where collector terminal over here it is common. So we call this one is a common collector arrangement where R1 and R2 network are giving a biasing, and where across I will take a emitter terminal across which I take output. So this is my output, and this is my input, and input terminal and output terminal which are connected to DSO or CRO oscilloscope which I have it. So in the channel A I will see my input, in the channel B I will see my output. And here the design of the common collector amplifier means I have to know what will be the value of R1, and I have to know what will be the value of R2, and I have to know the value of R, L, R, E. I have to calculate individually. So first of all, to calculate common collector amplifier design, calculate the resistance values means the designing of the common collector amplifier where I have to take the transistor condition as a reference. Right, which transistor I am taking over here from the data sheet. I have seen the range of the collector current. So that is IC range is given around 2 to 3 milliamperes. So my choice is around 2.5 milliamperes for the transistor. I took it, and if the same point, if I mention it over here on the characteristics, same point in the characteristics. So this is my DC load line where y-axis is my IC collector current through the transistor, and x-axis is the voltage across the transistor, collector and emitter. So this is my operating point where it will be the value of collector current and where it will be value of collector to emitter voltage. So this is called a VCEQ, and this is called a ICQ. ICQ. So as like we observed that the collector current it will be around 2.5. So let me fix that same value 2.5 over here. So this is what X and Y notations. That X value is nothing but the voltage which you are able to observe. As we apply supply voltage is around 12 volts. So there is a max voltage the transistor may get it around 12. So max voltage the transistor will get it around 12. So it will be at the middle as we considered. So it will be around 6 volts. So as 6 volts is appeared over here across the transistor, and the current which is flowing to be considered around 2.5. So the current over here it is considered around 2.5. So those two things that I am considering as the initial conditions for the transistor. Based on the conditions, we have to adjust my biasing components R1, R2 and RE. So here let me finalize the operating point values. There will be X value is around 6 volts and Y value is around 2.5 milliamperes. 2.5 milliamperes. So based on this operating point, we'll do the design, and whatever the output network we have it. Let me take the output network reference over here. There will be a VCC, and my transistor is connected as it is, and there will be emitter network over here. Emitter network, which if you take in the example, there will be 12 volts over here, and the 6 volts is dropped. remaining 6 volts need to be dropped over here across the emitter terminal. So when we are expecting 6 volts over here and conducting the same current, quotient current as the collector current, almost it will be the same, emitter current also same, it will be 2.5 milliamperes is conducted. 2.5 milliamperes is conducted. As we know, this much current is flowing through the resistor, need this much voltage drop. For sure, the resistance over here it should be V by I. As it says, there will be 6 volts we are expecting when the current is flowing through this one, 2.5 milliamperes. Then definitely the resistance of this much need to be kept over there to maintain the operating point where exactly we are expecting. So it says that 2.4 kilo ohms, that much resistance I have to keep it so that the operating point may be fit over there in the particular location. So as we see, whatever the value we keep it over there value to the simulation as per the design which we have done it. So this is the first phase where I have calculated RE, where the RE value is around 2.4 kilo ohms. So after that we'll do the calculation for the R1 R2. So we'll go with the calculation of R1 R2. So there R1 R2 network is like a biasing network which takes around 12 volts and has to generate some voltage to the transistor. This is where my transistor is kept, and emitter will be around 6 volts. Emitter needs around 6 volts, and the transistor also needs around 0.7 voltage. Unless 0.7 volts is given to the transistor will not come out of the cutoff. So it needs around 0.7, and there is a drop around 6 volts is required to the resistor. So totally, so this is what the electrical node which need to be pumped with the voltage drop around 6 plus 0.7, around 6.7 volts. So as I can say, this is my biasing circuit. This is my biasing circuit. Need to generate this much voltage. So from this, I can say this is just a voltage divider network where it divides the total voltage by R2 by R1 plus R2 times of the total voltage is around 6 volts, around 12 volts is applied into 12. So where total voltage is divided into this fraction, and where we expect around the 6.7. As per this equation, 12 times of R2, it will be around 6.7 times of R1 plus 6.7 times of R2. So as per this equation, 12 R2 is equal to 6.7 times of R1 plus 6.7 times of R2. If you solve this one, 5.3 times of R2 is equal to 6.7 times of R1. So from this, R1 is equal to around 0.8 times of R2. Yes. So this will be the basic condition that I have to follow, where R1 should be 0.8 times of R2. Yes. and I have to solve another equation also, because like I need to solve two parameters, so I need two equations. One equation is the voltage requirement point of view, it's around 6.7 is required. We solved that and we got one equation. This is first equation, and let us solve that another equation. So let us solve another equation. I will be going with the third equation. Let me redraw the circuit as it is. And where my transistor circuit is this one. Transistor circuit is this one. Where emitter resistance around we got it and calculated around 2.4. So there around 2.4 kilo ohms is required. So what I do is, instead of connecting this entire network to this one, I will be simplifying that input resistance offered by this network. So if this resistance where it conducts the current of IC, the branch where it conducts the IC, I will be moving into this branch. I will be moving into this branch where the current is IB, where the current is IB, where my current is IB, where my current is IB. So whenever I am trying to move the resistance which is there at a flow of current IC into the flow of current IB, which is exactly beta times or HFE times less, I have to scale my resistance that many times. So what I do is, I can put my resistance over here with that many times. So beta times in the sense, I will be getting a beta times of 2 point beta times 2.4 kilo ohms. So now I can erase this entire network. So this much resistance offered by this network, now it will be connected as it is. So this is the simplified network where the current which is flowing over there, it will be obviously IB. So previously over here the resistance value of 2.4k which conducts the current around the IC, now this is the branch which conducts the IB. So now we have to remember one thing, there will be R1 network, R2 network, and there will be R input network of a transistor. These three to be connected such a way that the most of the current should go into the R2 branch. So most of the current should go into the R2 branch. Most of the current has to go into the R2 branch. So very less amount of the current should go into the base branch, because when the current is more, if the more current is flowing into the transistor expects the beta times of IB current, so it will be expecting more. When that much current is not pumping, the transistor may be going into the saturation. So where my better solution always the design of R1 R2 network such that very less amount of current should be flowing into the base such a way that R2 need to be maximum, R2 will be minimum, less than times of the resistance which you have it. So when this resistance is minimum, most of the current will be flowing, as always current flows in a low resistance path, which chooses low resistance path. So from this beta times of 2.4 kilo ohms, right? And from this R2, if I solve it, less than beta of this transistor is chosen such that it will be 100. I'll show it in the simulation. So 100 and 2.4 kilo ohms. So it will be approximated into the 10 times of 2.4 kilo ohms and less than 24 kilo ohms. Yes. So when when I feel that the R2 resistance should be less than 24 kilo ohms, as per that availability that we have it in the lab, we have 22 kilo ohms in the lab, so I will be keeping 22 kilo over here. I will be keeping 22 kilo ohms over here. So 22 kilo ohms over here. So as like availability of the lab says 22 kilo ohms is the R2 resistance that I need. So here approximately I will be taking 22 kilo ohms over there in the lab. Yes, and if I substitute over here 0.8 times of 22 kilo, it is around 17.6 kilo ohms, and I have that the resistance which is there in the lab is, I have it around 18k. So 18k or 18.3k. So I will be keeping 18.3k in the lab. So 18.3k I will be taking it over here with the R1, R2, RE. I'm trying to connect it over here for the transistor circuit for giving a proper biasing, and where my input is connected to the base, and taking the output at the collector terminal with a proper arrangement. So where keeping DSO, I will be verifying my input signal sign and the same kind of output signal also with the gain 1 or not. Let's verify. So this is the circuit as it is. I have it here in the multisim. Let me do run. So input is given around like 5 volts. Input is given around 5 volts. Input is given around 5 volts. Now let me verify the output. Input is given around 5 volts. So now output is if I see this one, output is, so this is the channel A, 5 volts per division, 5 for this one, 5 for this one, totally 10 volts. So input is not 5, it's 10. So 10 volts is given as the input, and from the output from the output 5 volts per division for the output channel B, 5 another like 2 divisions that we have it, 5 plus 5, it's around 10 volts. So output is also like 10 volts, where I can say V input is equal to 5 volts, sorry 10 volts, and V output is at 10 volts. So from this I can calculate the gain, it is around 1. As we expect the common collector amplifier, the gain is equal to 1. So we'll be getting the gain equal to 1. So gain point of view, what we are expecting, that is simulated and we got it.